Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 103 Waves and Oscillations. Today it is the 23rd lecture of this course and the topic is Doppler Effect. First, I will give the learning objectives. At the end of this lecture, the student will identify that the Doppler effect is the shift in the detected frequency from the frequency emitted by a source due to the relative motion between the source and the observer. Also, they will be able to calculate the shift in the sound frequency for these three different cases. For example, they will be able to calculate the shift in the sound frequency for an observer moving either directly towards or away from the stationary source. Also, they will be able to calculate the shift in the sound frequency for a source moving either directly towards or away from a stationary observer. Or for the third case, if both source and observer moving either directly towards each other or directly away from each other. Also, they will be able to identify that for relative motion between a source and a sound observer, motion towards tends to shift the frequency up and motion away tends to shift it down. In this course, we are following the book Fundamentals of Physics by Holliday, Resnick and Walker, 10th edition. In this lecture, I have taken some of the figures from this book. Okay, we will start with the background of this Doppler effect. For example, a police car is parked by the side of the highway, sounding its 1000 Hz siren. If you are also parked by the highway, you will hear the same frequency. Now, if there is relative motion between you and the police car, that is either towards or away from each other, you will hear a different frequency. That is due to the relative motion, and that relative motion can give rise to these two following cases. For example, if you are driving towards the police car at 120 km per hour, for example, you will hear a higher frequency of 1096, that is an increase of 96 Hz. Or if you are driving away from the police car at the same speed as we have taken 120 km, you will hear a lower frequency of 904 Hz, that is a decrease of 96 Hz. Now in this lecture we will see why these numbers are changing due to the Doppler effect. Now, one can say that these motion related frequency changes are examples of the Doppler effect. Now, this Doppler effect was proposed in 1842 by an Australian physicist, John C. Doppler. And this Doppler effect holds not only for sound waves, that will be part of our discussion in this lecture, but also for electromagnetic waves including microwaves, radio waves and visible light. But in this lecture we will limit our discussion to the Doppler effect with respect to the sound waves. Okay, so we start with this heading, that is, we have a sound source and an observer, and both are stationary. So the source will produce sound waves as represented by these spherical wavefronts. Now we call this a sound source because inside this motor car there is a driver, and he produces sound waves with the pressure horn, and those sound waves are propagating in the medium air with the velocity v. Now this is the representation of the sound waves which is produced by the source, which is this motor car. Now that motor car, or we can say the source, is at rest. That's why Vs, S stands for the source and V for the speed, so it is stationary. Now though this V represent the speed of the sound waves produced by the source. Otherwise the source which produces the sounds is at rest. The observer is represented by this cartoon. Now this man will detect the sound waves which are emitted by the source, and this observer, the speed of the observer is also at rest, that is, the person is not moving. So when both the source and the observer is at rest, and the source is producing sound waves and the observer is receiving or detecting, or we can say hear the sound waves. So if both observer and source are stationary, the observer will observe a frequency equal to the frequency of the source. That is, there will be no shift in the frequency. That is, whatever frequency of the sound waves produced by the source, that frequency will be observed by the observer. And the frequency, in this lecture we will use f for the frequency of the source and f prime for the shifted frequency, or the frequency which is received by the observer. In the case when there is no relative motion between the source and the observer, there will be no Doppler effect. So for Doppler effect, relative motion is required. Otherwise, when the source and the observer both are at rest, there will be no shift in the frequency, or we can say no Doppler effect will observe. So from here we will start our discussion. That is, we will discuss the various possible situations in which there is relative motion between the source and the observer. So in the first case, if there is relative motion between the source and the observer, now for example we have a situation now where a source of sound, that is, this motor car is producing sound waves as represented by these spherical wavefronts, and this observer is moving towards the car. Now there is a relative motion now because the source again is at rest, but the observer is moving. We can have another situation where the observer is moving away from the stationary sound source. That is, we will discuss these both cases together just to make the understanding clear. So these are a situation in which observer is moving either towards the source or away from the source. So when there is relative motion, there will be shift in the frequency as produced by the source and received by the observer. So the two frequencies apparently will not be equal. So we are discussing the case when observer moves and the source is at rest, that is, the motor car is stationary in both of these situations, and the observer in the first case is moving towards the source, and in the second case the observer is moving away from the source with uniform velocity, and those speeds are far smaller than the remember, in this whole lecture we will be discussing this motion small compared to the sound speed, and also the motion is uniform. So what the observer receive when we have such situation in which observer is moving towards the source and observer moving away from the source. So in these both in both of these situation, he will detect a frequency which is not equal to the frequency emitted by the source, that is the frequency of the sound waves. So in both of these cases this will hold, and that is because there is relative motion. The second thing, why we are discussing these A, B and C, because in all these discussion we will be just concerned with the frequency, speed and the wavelength. So there are three parameters that will either change or remains the same when the observer moving or when the source is moving. So the speed of the sound waves, those are emitted by the source, and the speed at which the observer collect those sound waves. So the two will not be the same, because in the same medium in which the air moves with the velocity v, the observer is also moving with some velocity v. O means velocity of the observer. So we can say that the speed of the sound waves will not be the same as produced by the source and as received by the observer with its prime and unprime. But this velocity v prime in received by the or collected by the observer will be either increase or decrease. So in the first case it will be increased by an amount equal to the speed of this observer moving towards, and when he is moving away from the source, so that he will receive sound waves with a velocity somehow lesser than the speed at which the source is producing those sound. So this v plus v naught will be the case for this situation, and v minus v naught will be the situation when we are discussing this case. Now the wavelength prime and the wavelength of the source sound waves, those will be equal, because that does not depends upon the relative motion inside that medium in which it is traveling, but those lambdas, or we can say the difference between two wavefronts, will remain the same. It is the observer who is moving, so in this situation lambdas will be the same. So if we just collect this information and want to find out that shifted frequency, so that we know by definition frequency is equal to velocity over the wavelength. This prime represents that we are interested to know the frequency received by the observer in both of these situations. As I have discussed that v prime will be equal to v, which is the velocity of the sound waves produced by the source, plus the speed of the observer, which is moving towards the source or moving away from the source. So we can have these two situations for these two figures. So if we want to calculate how much that frequency is shifted, that is, we need to find out this frequency in terms of the source frequency. So for that we need to start with this expression as given in the point C, that is the two lambdas are equal. So by definition, if we want to write this lambda prime, that will be equal to v prime over f prime, and that is equal to lambda, which is v over f. So if we put the value of v prime from the second second bullet, so that this v plus v naught or v minus v naught for these two cases. Now if we just cross multiply this term, and we will be having an expression for the shifted frequency or the apparent change in that frequency, and we can see that f prime is not equal to f, but it is the two are related by this ratio. So if we see here, that is in this first situation where we will write V plus V naught, so that means the frequency received by the observer will be somehow greater than the source frequency, because we need to add some amount of velocity so that the numerator will be greater than the denominator, and this V prime, F prime will be greater than F. In this situation, we need to subtract the speed of the observer at which it is moving away from the source, so that if we see this V and this V is the speed of the sound waves produced by the source, so that V minus something will be smaller than the denominator, and hence this F prime will be somehow smaller than the frequency of the source. So in this situation, as he is moving away from the source, he will record somehow lesser frequency than the source at which the produces those sound waves. So there is a frequency shift due to that relative motion. Remember, in both of these situations, we are discussing when observer moves and the source is at rest. So when source is at rest, we have this situation, and based on these things we can find out the shifted frequency. Now we will be now discussing a situation in which the source is moving and the observer is at rest. If there is relative motion, as I told you, between the source and the observer, so that will give rise to a Doppler effect. That is, the two frequency emitted by the source will not be equal to the frequency detected by the observer. So now in this situation we have these observers, and they are detecting the sound produced by these motor cars. In the first situation, the motor car is producing the sound waves and it is traveling towards the observer. And as we have discussed on the last slide, when the observer was moving either towards the source and or moving away. So in the same way, we are now discussing that the source of sound is moving towards the observer, and in the second situation the source is moving away from the observer with uniform speed. Remember, the speed is far smaller than the acoustic speed, or we can say the sound speed. As next time when we will be discussing shock waves, so in that situation we will see that when the speed of the source is almost equal to or greater than the sound speed, so in that situation the equation for the Doppler effect will no more be valid. So remember, these are smaller speed at which the source is moving, but still we see now that the lambdas will be changing instead of the velocity. So now we have this situation where we have moving sources and observers are at rest. So what the observer received here, the parameters. The first thing is, in either of these two cases, as done with the stationary sources, the frequency will be shifted because there is a relative motion. Now the velocity received, or the sound waves received by these observers now will be having the same velocity as produced by the source. That is, the sound waves produced by the source is having velocity v, and the sound waves detected by these observers now is having velocity v prime, and the two will be the same because it does not depend upon whether the source is moving. The speed depends upon the medium properties, and once the properties are the same, it just produces the sound waves at a different position relative to the observer. So due to that situation, the lambdas are now changed because of this relative motion. Why? Because this car is moving towards the observer and this car is moving away from the observer. So every time the source producing sound waves. For example, in this situation, now he produces let's say a sound wave here, and then he just keep on coming towards the observer. So the next sound waves the source produces, that will be somehow nearer to the first wave, and hence the distance between two consecutive wavefronts will be keep on decreasing, so that the lambda prime that is heard by the observer, that will be somehow lesser in this case, and in this situation it will be somehow greater than the lambda of the sound produces by this. So this will hear us a longer wavelength, or we can say sound with a smaller wave. So that we can say that the two lambdas are not equal, because for the first situation each successive wave is emitted from a position which is closer to the observer than the previous wave. As a result, the wave front heard by the observer are closer together. And conversely, if we say that when the source is moving away from the observer, each wave is emitted from a position further from the observer than the previous position, and hence we have the distance between these successive wavefronts is keep on increasing, and here it is keep on decreasing. So that this lambda prime will be equal to lambda, which is the source, the wavelength of the waves produces by the source, and minus delta lambda in this case, because it is keep on decreasing, so that lambda will be somehow lesser than this lambda prime will be somehow lesser than lambda, that is we need to subtract something. And this situation, these lambdas are keep on increasing, so we need to add something, that is delta lambda, so that this lambda heard by this observer will be somehow greater than the source wavelength. Now this is equal to what? Now this or we can say the distance between two successive wavelength is keep on decreasing, and that is equal to what? We know that S is equal to Vt, that is distance is equal to velocity times the time period, or we can say the time between two successive waves that is emitted by the source. So instead of writing this delta lambda equal to velocity of the source multiplied by the time, so instead of time we need to write it in terms of frequency. So we know that time is one over frequency, and that frequency which is emitted by the source. So we can then express this lambda prime as lambda minus Vs over frequency of the source, or in another word we can say that lambda minus Vst and lambda plus Vst, so that t, which is the time between two successive waves, so that can be expressed as 1 over lambda. Remember, you need to look for this situation, we need to subtract that Vs by f, and here we need to add that distance, so that it is keep on increasing. So in the same way we need to find out that shift in the frequency, and we know that by definition f is equal to v over lambda. These prime represent that we are interested in the frequency observed by the observer. So that now since we know that this v prime is equal to v, so v prime is equal to v, that is we need to convert this parameter in terms of the source parameter, and this lambda prime is equal to lambda minus plus Vs over f, so that we have written here. Now solving this expression, that is v prime is equal to v over lambda minus plus Vs over f, if we just use the definition of this lambda, that is lambda is equal to the speed over the frequency, so that after the next step, if we take the LCM here in the denominator, so that it will go up and we will be left with this expression now. So this is for the second two cases, that is when source moves and observer is at rest. In such situation we have the parametric changes like this, and hence the frequency observed by the observer will be shifted by this amount, that is, it is proportional to this ratio and the two frequencies are not equal. Now in this first situation, when the source is approaching the stationary observer, we need to subtract something from the denominator which is equal to the denominator, but now it is different or smaller than by an amount v. So that means that the denominator is somehow smaller if we take v minus vs for the first situation, so that the overall this frequency will be greater than the source frequency, that is, the observer will record frequency of the sound which will be greater than the source frequency. And in the second case, when the source of sound is moving away from this stationary observer, we need to add this Vs, because after each successive wave the source is keep on moving away from the source, so we need to add that Vs as we have discussed here, so that the denominator will be greater than the numerator, and that is the frequency received by the observer will be somehow lesser than the source frequency. So in this way we can discuss the Doppler effect in all the four cases. Now if we discuss this Doppler effect through a general equation, that is, in the first case we discussed that the observer is moving either towards or away from the stationary source. On the second slide we have discussed that the source is moving either towards the stationary observer or source is moving away from the stationary observer. So in either of the observer or the source is moving, or both are moving, the emitted frequency f and the detected frequency f prime are related by this general equation. That is, with this general equation we can limit this to either of the four cases that we have discussed. For example, in the first two cases we have said that the source is at rest, so by source is at rest means we need to make this Vs equal to 0. In the second two cases we have discussed that the observer is at rest and source is in motion, so when the observer is stationary we need to make this V naught equal to 0. If both are moving we need to use the whole equation. So we can limit this equation to either of the cases that we have discussed. Now this equation implies to all the four mentioned cases as we have discussed previously. Also the sign of Vs and V naught, that is, Vs represent the speed of the source and V naught represent the speed of the observer, depends upon the direction of their velocity, as we have discussed, whether they are moving towards each other or moving away from each other. So in that situation we need to take care of the negative and positive sign of this equation. Now you need to go through the assignment part following your book and going to the module 17.7, the Doppler effect, where you will find problems from 55 to 67. You need to solve this problem in order to clear the topic Doppler effect. And with this, I thank you for your time.